Well, good afternoon, everybody, and hello to everyone online. I'm Andy Hooper. I teach here at the University of Leeds, and I'm going to be talking, as it says here, about time series InSAR. Okay, so I heard that, I know, apologies that Tim had to move his lecture this morning, but I think most of you made it, so you're all aware of what InSAR is, if you weren't already, hopefully. So I'm going to dive straight into the kind of time series aspects of it. Okay. So I start off with a motivation. So why do we do time series InSAR? It might seem obvious, but maybe it's a bit more subtle than you might guess. So you've seen examples like this already. This is why I call it a good interferogram. This was an earthquake that occurred some 10 years ago now. The interferogram was made, and you can see lots of fringes. There was lots of deformation. Obviously, it wasn't good from the point of view of the earthquake itself, but from the point of view of the image we can make, it's a very nice interferogram because you can clearly see the signal, right? So the signal to noise is really high. So that's because, first of all, there's good correlation. There's very little noise in the interferogram itself. And this is, I think, even before filtering. Okay, so it's just kind of raw interferogram. And there's a lot of deformation. So even though there will be other signals, like atmosphere being a dominant one, a chief one, you can't really see that, right? It's really dominated by the signal. That's great. You can unwrap it and very clearly where the deformation is. There's a large amount of deformation here on the order of meters in line of sight. Okay, but that's not really very typical of most interferograms that we work with. Not least of all because mostly we're working at the moment with C-band data from Sentinel-1. And that's the workhorse. Of course, that's about to change with the recent launch of InSAR, whether that which is an L-band supply. That will help. But typically, this might be the interferogram we look at. So it's poorer for a couple of reasons. This is here, sorry. So it's dominant. There's atmosphere here, and actually atmosphere is dominant. So although there is deformation here, it's a very low rate of deformation. It's just tectonic, and you can't really see it. All you can see here is the atmosphere. And then there's also some noise, right? Just some decorrelation noise in there as well. And it can be even worse, right? You can have even worse decorrelation, especially if you make interferograms that cover a longer time period, or there's a big separation between the orbits of the satellites, you get even more noise. So I would say this is really the primary motivation for time series InSAR, actually. Other ones. It's just to reduce these noise sources. So you can better select which pixels are coherent, so you can help that issue. And you can reduce these other nuisance terms like atmosphere and orbit errors, chiefly atmosphere has to be said. And this can be reduced by taking your time series and essentially filtering in time and space. DEM errors. So these come about typically if you have very large baselines. So I don't know if this was covered in your first lecture, but if the orbits are never exactly the same every time a satellite passes over, and if they vary a lot, then there's an effect caused by any error in the DEM you're using to remove the topographic phase. That hasn't really been a big problem with Sentinel-1 if you're using Sentinel-1 data, because baselines are very small, or have been, although that's changed recently with Sentinel-1A. And there's some other, I guess, nice issues, nice advantages of doing it this way is you can more reliably do the phase unwrapping step. And of course, you can get higher resolution. So Tim would have talked this morning about multi-looking or filtering. So typically, we don't look at data with the full resolution in which it's acquired. Typically, we downsample it in some way. And that's normally through averaging over pixels, multi-looking. But if you're interested in high resolution, then you can do that with the time series analysis too. Okay, and on top of all this, you can do the obvious thing, which is actually look at time variable processes. Okay, so as well as all this, if something's changing in time, you can actually look at that. Okay, so just to take those one by one. Improvement of coherence is just one example. These were the original interferograms. After you've applied your time series analysis, essentially thrown away noisier pixels, you get better looking images. Okay? And you can also, as I mentioned, you can remove nuisance things like atmosphere. So in this case, this is a study of a slow slip event that occurred down here. So this is actual what we think is a reasonable representation of the actual deformation. But then you see this is the atmosphere in the primary image. So it's the same kind of order and even overlapping spatially with that. So it's important to separate it out. And in this case, there was a large DM error, although that wouldn't be the case with Sentinel-1. And here's an example of high resolution. So if you move to high resolution, you can start to really pinpoint where your pixels of interest are, like on the side of the building. This is not sensible data, I should add. You can do very nice things with high resolution processing if you're interested in infrastructure. And here's one example of time variable deformation. So this is a volcano in Chile, and you can see, just looking at the line of sight, you can see this movement away, then towards, and then away again, associated with the volcanic activity that was taking place. Okay, so that's the motivation. And I'm going to dive straight into how we do it next. By the way, for those in the room, feel free to shout out questions anytime. Those online, I guess I'll pause every 20 minutes or so to take questions. Right, so there are two, well, according to my categorization, there are two main categories of time series methods. Okay? You may have heard of. One is persistent or permanent scatterer type techniques, and the other is small baseline methods. And there are some sort of subtle variations on that I'll come to, but I think that's fair enough to split them into these two main categories. So I'll talk about PS, persistent scatterers, or PS, first of all. Persistent scatterers is the general term. Permanent scatterers is a particular technique that's operated by Trey Altamira. So I'll talk about persistent scatterers as in general. Okay, so I don't know how much Tim went into this, but he probably mentioned that for every kind of resolution cell which becomes a pixel in your image, you're actually getting reflections of multiple scatterings on the ground. Okay? And so they've each got their own phase, and what you actually measure is the combined phase of all of them. So it's the coherent sum of all of these scatterers on the ground. That's fine. But if you come back later and these scatterers have moved around a little bit with respect to each other, then their phase will change independently. And when you add up all of these independent phases, you can get a very different phase sum. And that's what happens. This is just a simulation of 100 acquisitions where these are moving around with respect to each other. Well, I can't remember how much, but the point is, but if this wasn't wrapped, you might actually be able to see these changes. But because the data are wrapped, essentially it just looks like random values over time. Yeah. So that's the situation we have with these scatterers are all kind of contributing approximately equally, and they're moving around with respect to each other. And there is also a similar effect if you just change the angle you're looking at, okay? Because the path length changed to each of them, and yeah, so you'll add a certain phase to each of them, but a different phase to each of them, and you end up with another change which is too large. So that matters again if you have a large baseline. So if you have the change in the orbit characteristics is high, then that matters. For some satellites, that is the case, not for Sentinel-1 in general. Okay, so that's the case for the kind of normal kind of pixel that we're dealing with. But if you have a pixel where you have one scatter that really dominates, it's much brighter, and you kind of rerun the same simulation, in this case, the signal to noise ratio, the brightest one is 10 times brighter. So now they're moving around with respect to each other, and you can see that they're all contributing a little bit, they're adding a little bit of noise, but actually you can track the phase in time. So the amount of noise being added small enough, so it's much less than pi, 2 pi, then you could track this in time still. So that's the whole point, right? We're trying to find these resolution cells or pixels in our image that are dominated by one scatterer, brighter scatterer, and therefore throughout your time series of images, you can track this phasing. And that's persistent scattering pixel. So I'm using maybe a more general term than some might for that. But for me, it's when you can track, when the noise is small enough that you can track it. I call that persistent. Okay, so that's the pixels. Those are the pixels we're after. How do we find them? So the first step is just interferometry, right? You have to make some interferograms, and the persistent scatterers, you just make all of these with respect to a single primary image. You want to keep full resolution, and in fact, you might even want to oversample. So this is most people don't do this, but it's slightly preferred to oversample. You can, and then you want to make all the usual corrections. So remove the topography. I guess that's the main thing. So flatten it and remove the topography. You need to do that. Right. So that's just the first step. It's just interferometry. And I'm going to show sort of a number of plots like this where time is along the x-axis and this perpendicular baseline, which is a measure of how far apart the satellite's orbits are for each acquisition. So here, the red circle is every acquisition, and then the green lines are these programs formed. And you can see they're all made to one single primary image. And these are, for this particular example, which is Mexico City, these are the interferograms that were made. This is Sentinel-1 data, early Sentinel-1 data. Okay, so good so far. Something's happened to my, it should be a 5 or a P as well, not an F. I think it's a Mac to PC conversion. But anyway, this is just how we can consider the phase of each pixel as a number of different terms. So we can break it down into a number of different terms. Hopefully I'm a bit familiar to you from the InSAR talk we had earlier. So first of all, we have the deformation. Okay, this is what typically we're interested in. It may not be, but normally it is. Then we have an atmospheric delay term. So strictly speaking, this isn't the whole atmospheric delay. It's just the difference in the atmospheric delay between two images, which varies significantly, but much less than the total. Then potentially there's orbit errors, just because we don't know the orbits precisely, although these days we do know them pretty well, as I said. There can be a DEM error introduced just by the fact that our topography is not perfectly known, of course. So though we subtract it, some signal will be left behind. And then there's a sort of bucket of noise, which is mostly decorrelation. There's a few other things that go into that as well. Right. So what I'm defining as a PS pixel is just a low noise pixel. When this noise term is low enough that you can track the phase and time, that it's a PS pixel. So that's what we want to identify. So for every pixel in image, we want to come up with an estimate of this noise term. And I guess there's two different ways of doing that. And the original approach, which is still very much used today, which is based on a temporal model. And then there's another approach which is based on spatial correlation. I'll talk about both of these a little bit. First of all, the temporal model. So this is the original approach. So I guess a number of people worked on this at a similar time, but this is the results from Alessandro Ferretti, who's been a sort of prime mover in this field, I'd say. And these are the results for San Francisco Bay, as produced in 2004. Okay, so here what we've shown is in color is just the average velocity. So you often see this, although we're talking about time series here, and that means you have deformation measurement for every PS pixel at every time. One thing you can plot is then the mean velocity. That doesn't mean it has to be a steady state velocity. It's just the mean velocity over time. So that's what's being plotted here. And course, this is the Bay Area of San Francisco. There's lots of deformation due to tectonics there, but there's other things going on as well, substance and so on. Okay, so coming back to this question, how do we isolate the noise? So in this approach, the first step is to find pixels close to each other, think of PS pixels, and subtract the phase of each other. Okay, and by subtracting the phase, you kind of cancel out more or less the atmosphere, because that varies sort of slowly spatially, right? So points a long way apart have a very different atmosphere, but they're very close, they're very similar. And also the orbital error terms cancel out as well. So you're just left with these two things. This is what we're going to characterize, and you've got deformation and DEM errors as well. So these two terms can actually be estimated by modeling, which would then just lead this noise term. And how is that done? Okay, I'm just going to step back a bit now before I get to that. So going back to the actual operational algorithm, if you like. So the first step is to do some sort of selection, right? So at the beginning, you're just going to select the most pixels which are most likely to be PS. That can be done in some different ways, like picking the best pixel in a grid cell. And how do you determine what's a good pixel? Well, of course, it's based on phase, and we don't yet know, or based on phase noise, we don't yet know what that is. There's quite a good correlation between phase noise and something called amplitude dispersion, where amplitude dispersion is just the standard deviation. So in your time series of images, you look at the amplitudes, and you look at how the amplitudes of each pixel vary in time. So you calculate the standard deviation, and also the mean amplitude, divide one by the other, you get this amplitude dispersion. And as I say, it's a reasonable proxy for phase noise, but only if the phase noise is small. Okay, so for low end numbers of amplitude dispersion, it's a reasonable proxy for the phase noise. As soon as you get to larger numbers, so actually you can see already it starts to just really blow up. So yeah, if you get to 0.4, you've got no idea which phase noise you can see. But for low values, 0.2, 0.25, and so on, so it's reasonable. Okay, and it's good that it's reasonable, because for this algorithm to work, you need most of your pixels in your initial selection to be PS pixels. If most of them aren't, then the whole thing kind of falls over. Okay, so that's just on the initial selection, and then we come to this estimation step that I was talking about just now. So estimation of parameters, which are displacement parameters. For this, you need a model, and typically what we're really estimating is the velocity. So we assume it's approximately linear, and estimate the velocity each pixel pair. Another thing to estimate is the DEM error, as I mentioned. Okay, so just to make sure we're on track, we're talking about double difference phase here now. So we've already differenced, our interferograms are differencing in time, and now we're differencing in space as well. So we're talking about the arcs, if you like. So if these are individual PS candidates, then what we're looking at is the arcs, the differences between these pixels. Okay, so it's double difference in time, a difference in space. And the reason we did that was to sort of get rid of atmosphere, basically. Okay, so coming back to this figure I showed, this equation I showed before, we need to model these two terms. So you can model it in time however you want. The sort of default is typically just to assume that it's approximately linear. So each of these phase arcs is going to have a linear phase progression. Okay, so what do we actually measure? We plot versus time. We plot the actual phase that we have. We just have these values here. Okay, but because of the wrapped nature of the phase, to actually fit a straight line, which is what you do when you estimate velocity, you have to allow for the fact that each of these values could have integer number of 2 pi added to it. Right? So this this pixel will actually be up here. It could actually be up here, or down here as well. So actually fitting this line is not as straightforward as it might seem. It's not a linear problem. There are different ways of doing it. But essentially what you're trying to do is you allow for the fact you can add an integer number of 2 pi to every value, and then find the best straight line that minimizes the residuals overall. That's the idea. So this is actually, it looks like a nice fit once you've done this unwrapping, which is to add 2 pi or 4 pi some. But if you look at it back in the wrap domain, it fixes like this, right? Jumps down. Every time we get to here, it has to jump down, go up again. Okay, so this is done for every pair of pixels. These are your candidate PS candidates. Yeah. So the other thing you need to do at the same time is fit a model for the DEM error. And again, this is actually another straight line. I'm not showing you the kind of the unwrapped version, it's just the wrap version now. But these are the pixels, and I think you can see actually better in this case that this line fits very nicely. You allow for the fact that it's to wrap at that point there. So what does this line represent? We're plotting the phase here. So this is phase versus perpendicular baseline. That's E curve here, and this is the slope of that straight line. And in there you have these are basically constants. In there you have the DEM error, which is what you're estimating. Okay, it has to be said, doing this in 1D is not that bad. Doing it in 2D, so simultaneously estimating both the velocity and the DEM error is just a bit more time consuming to do, but you can do it. Okay, and so having done that, for each of these connections, you have an estimate of both velocity and DEM error. And then if you integrate over the whole network, you should get something consistent, right? So you integrate from here to here to here, I should get the same as if you go any other route around it. And of course you won't. Partly because of errors, but also because of blunders. Some of these will just be totally wrong. So during this sort of integration step, you have to allow for the fact that some points or arcs may just be incorrect, and you want to reject them altogether. Okay, so having done that, rejection and integration, then you have these parameters, so the velocity, DEM error, at the points rather than for the arcs. And that stage is sort of done, not quite, but these give you results. So you have DEM errors, which is probably what you usually may not be that interested in, but you'll have the velocity as well. So this is just one example of that. So these are just for the candidate pixels, the pixels most likely to be PS in the first place. Okay, so the next step would then be to try and densify that. So you want to go back and look at all the other pixels, check if they might be PS as well. And to aid in this, the first thing you do is estimate the atmospheric delay for each interferogram. So that's done by taking your good pixels, the ones you've identified, and filtering them in space and time, essentially, to get at what the atmosphere is. And you can subtract that from everything then, and then test every pixel in turn to see whether it's a PS. In the same way, I should say. So you make this arc, so you find the nearby PS, you calculate the phase difference in every interferogram, and then you see if you can fit a nice velocity and a nice DEM error to it. Yeah, I guess what I didn't emphasize here in particular. So how do you really decide it's a good PS? Essentially, if having fitted your model for velocity and DEM error, if you've got high residuals, then that implies high noise, and it's not a good PS. Okay, so these are results I showed you before. I guess I'm showing this again because I want to point out that it works really well in some areas, these areas, but not so well in other areas, right? One of the areas it works well in was urban areas. This is where everyone lives, it's where all the infrastructure is. Over here, it's in the mountains, the hills, there's one town over here. But generally speaking, there aren't too many buildings in this area here, and it doesn't work so well. So that's true in general for this approach. Okay, I'm going to stop my first Q&A. Should we start in the room? If anyone's got any questions in the room? Stage. Yes.
So you mentioned that in your integration stage, you're not actually going to have everything add up correctly because there might be some pixels that just aren't great. Is there any way that you can detect after that integration step, which pixels might be causing these problems, or does it just create a noisier?
Yeah, so that's actually sort of an important part of the process is to try and identify this. So you can integrate once, and then essentially look at where your biggest residuals are and do outlier rejection. There are different ways of doing that, but that's one way of doing it. So where's the worst residual, and then throw that one out and then try it again.
Just filter it down.
Yeah, actually just start one by one. Do that, yeah. Otherwise you're right. Otherwise you actually kind of throw off your whole estimate. Right? You will understand that.
You said that you should model the deformation, get the signal replaced. So how you do to deal with the, I guess there would be a bias of the model of the deformation. If you have no clue about how is the deformation, you want to get this information, but how you deal with that?
So do you mean if the deformation is not sort of linear in time,
or you have no clue about the deformation?
Okay. Well, in principle, you don't need to know the deformation beforehand because you're doing exactly that. You're estimating it. So that's one of the outputs indeed that you want to get at. So it's fine as long as it's approximately following the model. So once you've picked yes, you can then go back and actually look at how it varies in time. And as long as it hasn't deviated too much from this sort of linear model and it's been picked, you can then actually look at the true time history, which may not be linear. And that's not really a question, but I mentioned that a lot. But yeah, no, the whole point of this is indeed just when you have no a priori knowledge of the actual measurement to estimate it. That's the point. But the first step is just to identify which are the good pixels, and then you can sort of look more in detail at what the measurements are that you've actually got. Does that answer your question at all? Yeah.
I guess for the first stage of selecting these persistent scatterers, the amplitude dispersion, and is that limit in terms of the amplitude dispersion? Is that a hard limit? Is it if it's there are no signal that exceeds that it can't be chosen for persistent scatterers? Do you have to have that? Is all relative according to the image? I guess also following that, you say the nearby pixels as well. We talk about spatially they're nearby. So if there actually is a limit also to that as well, they're quite spatially distant. You can't actually do this estimation at all. I guess the main point of that is there just some landscapes where you cannot get good persistent scatterers?
Yeah.
And you can't even use characteristics.
It's a great question. It tees me up nicely for the next, pretty much the next slide. Yeah, absolutely. So, there can be areas where you just don't have any of these pixels with a low enough amplitude dispersion to be selected. And then you can start to run into problems if you have distances which are more than a couple of kilometers. Even a couple of kilometers might be too much, depending on how many separation there is. So, yeah, no, absolutely. It doesn't always work.
From the estimation of this atmospheric noise, basically, if you're considering a very small signal, not a very big signal, and the atmosphere is basically not varying. So how this method will work?
Yeah, so it may well be, if you look at a very small area, that there's not a lot of ionospheric variation, but there's still likely some tropospheric variation. So that varies more on very small scales, actually. So yeah, I mean, And I've never looked at an interprogram without atmosphere. There's always an atmospheric signal there. Sometimes it's huge, and sometimes it's not so bad.
No, basically, there is no difference between the pixels. So how we will not be able to differentiate, like, estimate this atmospheric noise and then
Oh, okay, right. So yeah, so this first step of differencing cancels out most of it, but not all. I mean, there will still be some atmosphere there. Of
Yeah.
course. So once you've gone back and you've sort of calculated every pixel phases, you can then, I mean, the space, the filtering in time and space is basically on the assumption that deformation is smooth in time, and the atmosphere jumps up and down. So if you take a PS and smooth it in time, residuals kind of your atmosphere. You can then also take those residuals and filter them in space as well, because some of that will be noise. So get rid of that. That's how it's done. Yeah, but the signal. So when you sort of go back and the signal is still there, even though you cancelled most of it during the initial subtraction process, it's still there. Go back to the still. Yeah.
because the area is very small, so that there will be spatially correlated, like, so that method should be having a big area so that there is difference between the atmospheric noise and we can subtract it and estimate.
Okay, so your question is really about when, if you're really interested in what the atmosphere is, yeah, you can't estimate that well.
Where the small will.
Yeah, typically, if that's what you're interested in,
Yeah.
probably look at the big area. Yeah. Okay, any questions online?
You know what?
Oh,
I have like
okay.
12 questions here. I'm reading through them, so see. Which is the best way to have a good results by using the whole image or just the burst?
Actually, in principle, okay. So, have you got a microphone on?
No.
Okay. Well, I guess maybe people are like it. But the question is whether it's best to use a small burst or a bigger image. It actually doesn't fundamentally matter. Obviously, it takes longer to process a large image, but you can take any number of bursts and process them together. It's just a processing issue there, right? How you handle that.
The next one is from a geophysical perspective, how is the millimeter level surface deformation detected by InSAR quantitative inverted to provide meaningful constraint for reservoir parameters?
Yeah, well, I think you're going to get to this, right? And there are later part of the course. It's going to be all about interpretation. So I think I'll just skip that question for now.
Would it be better to select a different master image in the example of perpendicular baseline plot?
Yeah, okay. So in terms of how you select your primary image, it does make sense to pick one that's in the middle, right? Both in time, somewhere in the middle, both in time and perpendicular baseline. Right? So it helps to minimize these things because then you're minimizing the noise in general. Do that. Yeah.
U1 has to transform displacement from line of sight coordinate system to ground coordinate system for interpretation. What are the errors introduced?
Yeah, that's a whole other can of worms, really. That aren't really covered by this lecture, but
It will be in my lecture tomorrow.
anyway, brilliant. Okay.
So next one, this is nice question, but it's more. I summarize it. It is, they said you're not from the geotechnical remote sensing. We don't have that background, but over time I've been working a lot with InSAR, handling different processing issues, but always have problem in troubleshooting and getting solid results. Is that okay, or do you think understanding the theory is still important if I'm already able to process the data well?
I think understanding something about theory is important to be able to interpret your results. It is, I don't know, I haven't seen yet anyone come up with a sort of algorithm that's foolproof that just always works or tell you when it hasn't worked in a reliable way. So inevitably you have to kind of look at the results and scratch your head a little bit and think about what they're telling you and whether you can really believe it. So I think actually understanding is is important still.
Is it always best to use a DEM with the highest possible resolution, or is there a maximum needed resolution?
So if you have one that's of the same resolution as your data, that's good to use, but it's not essential because one of the things you're estimating in this approach is this elevation, this DEM error. So actually, I mean, in principle, you could not remove a DM at all, and it might still work. You could just estimate the DM from the PS. So yeah, but it would make it more difficult.
When conducting a SPOS InSAR in mountain regions, I frequently encounter large-scale deformation anomalies, particularly in valleys, which manifest as abrupt jumps in the temporal dimension in time series. I wonder whether this is due to the limited resolution of the DM or the influence of local water vapor. How can these anomalies be eliminated?
Yeah. So without looking at the particular case, of course, it's not possible to really say what might cause those anomalies, but indeed it could be local atmospheric conditions. It's quite a likely one. If you have some sort of typically, I would say your DM it wouldn't just be unreliable in the valley; it's probably be unreliable elsewhere. So you might say affect the throughway. So yeah, but the other thing it could be is related to something I'll briefly mention, which is a phase bias term, which in vegetated regions, which typically get in the valley, might add an extra signal as well.
Does one have to resample the DEM raster to match the resolution of the radar image?
Yes. Okay. Shall we leave it there for now? And, yeah. Carry on. Thanks, Sammy. Okay. So moving on to the other PS method. How are we doing time? This is based on spatial correlation, and this addresses the question that was asked in the back there. So I guess this is part motivated by my PhD work. So I got interested in this approach. I was interested in volcanoes, so I applied that PS approach I just described to you to a volcano. This is Long Valley caldera in California, and these are the results I got. So I got really nice results for the town of Mammoth Lakes down here. There's a few buildings there, and really nice results over this obsidian dome. So obsidian is really good for scattering as well, as it turns out. But over the rest, I got nothing. And why is that? So it comes back to the point that was raised already. You need to have a good distribution of these high amplitude PS, so PS with a low amplitude dispersion, to establish your network in the first place. If they're too far apart, then this assumption that you cancel the atmosphere when you take the difference, it doesn't work. So, a point here and a point here, the atmosphere will just be too different, and there'll be a significant phase turn left. Okay, and there's a maybe more subtle point as well, that you might have very non-linear deformation in time, which might cause it to fail as well. So there's another approach which is based on using spatial correlation to kind of get through the noise term rather than this temporal model. Yeah, so it's a more maybe a more general approach. The pre-processing, however, is the same. You just make a bunch of interferograms, all with the same primary image. Hopefully, somewhere in the middle of this image, the primary is hopefully somewhere in the middle, so minimizing both temporal and perpendicular baselines. Okay, so coming back to this equation again, we're trying to get at the noise. So how do we go about that? So it's slightly different here. And the approach taken is to estimate the spatially correlated phase around each pixel of interest. So if you're trying to test whether this pixel is red square is a PS pixel, you take all the other potential PS pixels around it and in some way take an average of that. So it might literally just be the weighted average, or it might be some other filtered version of that. But you're trying to get at what would be the spatially correlated part of the phase at the pixel of interest. Okay, and if you subtract that off, you subtract nearly everything. So the assumption is that deformation is spatially correlated. On the whole, that's true. certainly for chip is significant. Atmosphere is definitely spatially correlated. Orbits is as well. And some of the DEM term might be spatially correlated, and some might not be. So you get rid of nearly everything, which is nice. And you're just left with the noise term that we're trying to get at, and it's part of the DEM area that's uncorrelated in space. Okay, so you can imagine DEM might be very broadly wrong, right, in a correlated way, but it might for each pixel of interest. We will have a specific error as well. Okay, and as before, you can model this DEM error, or the uncorrelated part of it, as I showed you before. So again, it's the same plot. Right? You have a perpendicular baseline, and here now I'm plotting original phase minus the correlated phase, and you get something like this, right? And this would be a good pixel, whereby once you've fitted your straight line with wraps, once you've fitted that through it, you've got very small residuals. So those residuals are what tell us what the noise is. Okay, so you can convert those residuals essentially to temporal coherence. So when they're very small, you get closer to a coherence of 1, and when they're very large, you get coherence close to 0. Here's the line. I guess one nice advantage in terms of processing effort is that it's much easier just to fit a single 1D line rather than simultaneously trying to fit 2 of them. Yeah. Okay, so there was some of you may have spotted a slight issue. First of all, I said to estimate whether this is a PS pixel is you take some average of all the other potential PS pixels around. And the first time you do this, you don't know what the other pixels are. Yes. So you just have to take a guess the first time. But then having done it once, you can iterate. Okay, so each time you iterate, so yeah, it says here, right? So you can weight them. Having done it once, you've got some idea whether each candidate pixel is a PS pixel, and then you can weight it based on that likelihood and get a better estimate of the correlated phase, and then re-estimate DEM error and temporal coherence. Okay, if you iterate that a few times, then you get a result that's kind of converged. Right, so at that point, you can then select which pixels are or aren't PS based on this phase noise, and then go back to original phase in the same way you would for the other approach we talked about. You go back to the original phase, except that you've already estimated this, so you might as well subtract the DEM error term. So these are the results for that long valley example, actually. So these are all data. These are from InSAR. Sorry, from ERS, yeah, back in the 90s. Right. There's one sort of extra step you have to worry about here, though, which is the phase unwrapping. So where you have a temporal model, that kind of does the phase unwrapping for you, right? When you fit that velocity in time, you are, in fact, unwrapping the phase, having to add 2 pi integer numbers of 2 pi to each value. These results, they're not unwrapped, so you still have to unwrap them. And of course, you can just do that using a standard unwrapping algorithm that Tim would have talked about. But actually, you can do slightly better because you have more data, so you kind of have a third dimension of data now. So the 2D unwrapping problem, I'm not going to go into 2D unwrapping problem in any detail at all. But typically, it involves identifying what are called residues, right? So it is your data at each of the actual points, data points will be just the crossing points of these lines here. If you integrate around, see whether you go back to 0, you get these so-called residues, and by connecting up residues, this helps you to figure out what your integration path should be in your phase unwrapping. Okay, I'll say no more than that. Only to say that if you take a whole time series of image, then you've got more. You can look at time dimension as well, and calculate these residues in space and time. So that helps. Okay, so then you have your unwrapped phase. So essentially these are interferograms, but kind of point-wise interferograms in time, all with respect to the same time. And then just like in the other approach, you can estimate the spatially correlated errors. So, sorry, this bit isn't actually. So there's still part of the DM error that hasn't been subtracted like it was in the other approach. So you have to estimate that. And it's easier to do it once the data are wrapped because that's just a linear problem. But then you have to filter in time and space just as you would in the other approach. And this is to remove atmosphere. And you get a result. Okay. So applying this approach rather than the original approach, then I got one more points, so I was happy with that. And you can look at the time series. So as I mentioned before, even if you have assumed that the model is sort of linear in time, which wasn't the case in this approach, but even if you have, you can then actually look at the data at the evolving time. So the InSAR data here in red, right? So you can see that actually it's not a linear evolution with time. Volcanoes rarely are. So, yeah. Anyway, so all good. So this is just to sort of prove that it matches other data that I mentioned there. Okay, so a couple of other points. It's a good idea to have some estimate of the errors associated with your measurements. So there's different ways of doing that, but certainly if you're looking at velocities, you can come up with the errors for that just by bootstrapping. So fitting a line multiple times through different, you select a different, okay, so for each pixel you select a different number of images each time and is a line, and you do that multiple times. That's called bootstrapping. So you get errors like this. So this is a PS result for Bangkok, and these are the errors. Great color scheme, but anyway. So the errors are lowest here, as you might expect. This is the reference point, and then they increase as you get away from the reference point. So that's as you would expect. This atmosphere is growing away from that. There has to be said. This is basically the assumption that your rates really are linear in time. So any non-linear deformation will get mapped into this as well as an error, even though it's not really an error. That's worth bearing in mind. Okay. So what about these two different approaches? You basically get the same results. If you're operating in an urban area, you pretty much get the same result whichever approach you use. So don't worry about it. So maybe there are some exceptions. This is one example. Someone else ran a comparison, and this was a new build area where some pictures were picked up by one approach but not another. That's a rare exception, I'd say. Okay, but obviously in rural areas, I definitely point towards the spatial. Okay, a word about interpretation, because you're getting real point-like measurements here from PS, which is nice. But if you think about it, some of them will be off infrastructure directly, and some of them will actually be double bounces off the ground. So I don't know if this was covered already, but you get really nice reflections if you bounce off the ground and off a wall. So as long as you have a kind of vertical wall and horizontal ground, then you get really nice reflections. So lots of our PS points are these double bounces. And that matters if they're off the ground, because if you have something like compaction of the ground, right, you might get the situation where these double bounces show deformation, but reflections off structures themselves, which might be grounded in a stable layer, so they're deep foundations, they might be stationary. So you can start to sort of tease out what kind of deformation is going on by looking where these scatterers are coming from. Are they coming from the ground, or are they coming from the building? And conversely, you have the case where the ground is stable, but the building is collapsing, its foundations are collapsing. Or you have a scenario where everything's moving because of some deep-seated deformation that's going on at depth. Okay, so just to summarize PS, it relies on these pixels that have low decorrelation in time. You do get results at high resolution, which is nice in some cases. You have to filter to reduce non-deformation signals. Good in urban environments, but can be applied in rural environments. Okay, that section was quicker. It's time for another Q&A. If there are any more questions in the room. Do you want to do a couple more now, Sammy? Or?
Yes. So, people can hear me. In the case of areas with dense vegetation, is it possible to apply a filter or something similar to increase the certainty and quality of the results?
So, I mean, a pixel that's dominated by vegetation just won't make a good PS anyway. Maybe this isn't really referring to PS, but so I guess the whole point about PS approach is to get rid of those pixels and just focus on those that have a good response, I guess. So that's what. In a moment, we'll come into small baseline approaches where that's maybe more relevant, I guess.
In my research, I usually use the same workflow, but when I change with different baseline setting, in baseline plot, I obtain completely different results each time. So, what is your comment?
Yeah, I'd be suspicious about your results there. Yeah, I mean, lots of things can go wrong, actually. So you do have to be careful, and there's a bit of an art to it as well, I'd say. But yeah, I guess if you're not getting consistent results, then it's a good thing to do, actually, just to check. If they're not consistent, that's a red flag.
How can temporal decorrelation that occurs when surface features change between the two SAR images, such as due to vegetation growth, snow, or even random motion, be addressed?
Right. So again, if you have vegetation growth, then it's not really going to be a PS, probably. But you can definitely have snow on PS pixels, of course. So persistent scatter pixels can temporarily be decorrelated by like snow or ash or someone parking their car in front of it, whatever it is. So yeah, it's a whole other layer of complexity to try and figure that out. And I don't think I can get into that section.
Last one, why do we need a reference point to anchor results? Aren't they already referenced to the satellite location?
Yeah, good question. No, they're not. So we're only ever measuring with InSAR something that's relative. So yeah, I mean, it's because the actual changes in range from the satellite to the ground can actually vary quite a lot because of the atmosphere. So we don't, and you can't get at the absolute because we're only measuring these sort of finite amounts between. In the case of Sentinel-1, it's like 2.8 centimeters is another RAM. So you don't know how many of those 2.8 centimeters the actual range has changed by. So you can't get at that not from InSAR phase at least, from range measurements maybe. So all we can do is say, well, let's not worry about the absolute. We'll just tie it to a point, and we get the relative information.
So one is about the future of stamps. So the question is long, but the question is about what would happen.
Well, just briefly, there is a future of stamps. At the moment, it's being converted to Python. So currently, anyone's used stamps, it's this old sort of MATLAB clunky version. So there will be a new version soon. There's a question in the room. So
so I wonder if you could go back to your slide about the convection for interpreting results.
Yeah.
So I didn't understand what you were getting. So what is? So would you get? So is this suggesting that we have the same signal for these different types of motion, or are these producing different, distinct types of signal that we're observing in our interrogation?
I'll probably went through that way too fast. So this is meant to be your sort of starting scenario, and then 3 different things can happen. And in each case, you get a different response. So you measure something different. So in the first case, when the ground is moving, this PS, which is bouncing off the ground, that would change, show deformation. But this one wouldn't, because it's banded and stable there. So the top one is not moving. Whereas it's sort of the opposite of this connection, right? So now the ground is not moving, and even though the house might be, probably wouldn't see much of a difference in this double bounce than you would for the friction from the top.
Okay, so in our InSAR map, what these will be reflected as is two persistent scattering points, and the one showing motion and the other not, even though they are close together.
Exactly. Yeah.
Okay.
Yeah. Yeah, and I mean, it's not what's commonly done, but you can try and figure out what's what, right? So the height helps you a little bit. So especially if you estimate the DMR, is it likely on the ground? That's off the ground or not? Sure. Okay. Time for coffee. Right. Part 2. Small baseline methods. I guess I've left less time for this, but actually, because it's quite straightforward in many ways. So what's the point of small baseline methods? Well, going back to this figure from before, this is a persistent scatter pixel, right? This is one that behaves really nicely over time. But we'd like to use all these other so-called distributed scatter pixels as well, right? So where we've got lots of scatter can be itself. So how can we do that? Well, the answer is it's obvious, really. You just make interferograms where, okay, you accept that there's going to be this decorrelation, but you just make interferograms where that's minimized. So that really just means making interferograms which have a small temporal baseline. So, yeah, in time, they're very close, but also a perpendicular baseline if you've got a satellite where that varies a lot. So you just try and minimize it. Okay, so the standard small baseline approach, or I guess there's a bunch of different small baseline approaches, but they all involve just making interferograms between your image pairs that have small perpendicular and temporal and Doppler, but that's not normally an issue these days. Don't worry about that. So perpendicular and temporal baselines, like this. Okay, it's just one example. So here again, time on the x-axis and perpendicular baseline here. So you can see all of these lines are made to kind of minimize these two things simultaneously. So there's no histogram being formed between here and here. That would make sense in time at perpendicular baseline. So you make these interferograms, you can multi-look them, which is you'll have learned about at lunchtime. You can unwrap them just using standard two-dimensional ways of wrapping. And then you can find pixels that are spatially coherent. So you can estimate the coherence in the standard way we do for interferograms. But then look for pixels that kind of have good coherence or a reasonable coherence in most interferograms. Now, having done that, you have to invert in some way to get to your temporal displacement. Okay, so it's really just conventional InSAR, right? I mean, you've got to select which interferograms you make, but typically you're always going to make interferograms that maximize coherence. So that's what we want to do. And then there's this sort of extra step at the end, which is just to find coherent pixels throughout your time series and do an inversion. And by inversion, what I mean is get this displacement relative to a single epoch, so a single prime. Again. And this can be done in different ways. You can use singular value decomposition. So the original SFAS algorithm that many of you have probably heard of uses that approach. You can use least squares, you can use constrain least squares, you can use one norm as well. And no doubt there's other approaches as well that you can offer. But anyway, you can convert it in some way to get a single time series. I'm just going to brief diversion into the meaning. What's the meaning of the AS in SFAS? It means and subset. Okay, so what that's getting at here is you might end up with a network where all of these, in this case, all of these red ones have been dropped. They're incoherent for some reason. So there's a break in the network at this point. You cannot connect across for some reason. So then you end up with sort of two isolated subsets. And the AND subset is a way to deal with that. So the original SBAS has a way to deal with that. So NSBAS and LixBAS that we'll be using in this course as well, for those of you who do the practicals. So it stands for AND subset, but not all small baseline algorithms have an approach to dealing with this. In some cases, you've got to be fully connected. Okay, so for this reason, personally, I don't like to use the term SBAS for this kind of approach in general. To me, SBAS is a particular algorithm. It's the sort of one of the it's one algorithm, one example, so say, of a small baseline approach. Okay. So SBAS is not, it's a particular implementation of this algorithm. Okay, getting back to the approach. So one of the nice things about using a small baseline approach is you have some redundancy, right? So you end up with this network. It's a kind of minimal case. If you have 3 acquisitions, you make 3 interferograms. But in principle, you only need 2, right? If you want to know what the deformation is with respect to that, actually you do 1, space 1 or 2, right? But because you have 3, you've kind of got some redundancy, which means you can check for errors. Primarily, what we want to check for is unwrapping errors. So one of these, if they've all unwrapped correctly, we can integrate around here. We'll get back approximately to 0. So add that one, and then subtract this one, you should get back to 0 if they're all unwrapped correctly. And if they're not, then you have some choices, right? You can say, well, we'll just throw them all out because we don't know which one is bad. But then if you have other loops as well, you can sort of test them independently in other loops to try and get at which one is the problem. So this is outlier. Okay, but just note that you won't get back to 0 exactly, and that's because decorrelation noise and also systematic biases can actually affect this loop closure as well. So you'll never get back to exactly 0. So never expect that. If you're coding this up yourself, don't look for values of 0. You have to allow for some small amount. Okay, so here's an example. This is from LixBAS, and this is an area in Japan. So first of all, this is just showing the LixBAS results. That's the kind of non-circle color. LixBAS results, and the circles are all showing measurements from GNSS. That's just to show us for validation, it's giving the velocities about right. Also, you can look at the time series. So the LixBAS time series here is shown in blue, darker blue. And again, there's GPS underneath that as well. You can see it's certainly not linear in time. Even if you could plot the mean velocity, it doesn't have to be linear in time. So within Comet, and many of you will be within Comet as well, I guess, this is the approach we've been using for our large-scale processing. And we started off looking at Turkey. These were some of our initial results anyway. So we could take both descending images and ascending images. Hopefully these terms mean something to you now. And calculate the mean velocities again, which we did for Turkey. And then you can decompose those into east-west and vertical. So I guess Tim talked about this a bit, but because we've only got two look angles, and basically one's more or less from the east, one's more or less from the west, we're not really very sensitive to north-south. So we actually take the north-south from GNSS in this case, and then just solve for the east-west vertical. Okay, so that's all very nice. We can go even larger. In fact, we've done this for the whole Alpine Himalayan belt. Now, this is for the Tibetan region. Again, just showing the eastward velocity. So we've done ascending and descending and derived this. Okay, variations in small baseline approach. So you can do phase unwrapping in kind of 3D approaches, or at least using this third dimension of time, which can help you improve accuracy. You can actually do full resolution processing. That's not common. So the standard approach relies on multi-looking first. You can do this. There's a few different ways of doing that, using single look images as well. Okay, that's nice because you get better resolution. That's important, but also sometimes you can find stable pixels which are isolated, right? So if you've got a good pixel which is surrounded by vegetation, if you just average multi-look, then you just obliterate that signal. So sometimes it's good not to do that. So one of these approaches is the stamps approach, and basically it's the same approach as PS, more or less, but it's applying this to small baseline interferograms. Yeah, there's a result. I mean, just to show you that. So in this case, these are PS pixels, these are small baseline pixels in one interferogram. They give you the same signal, slightly better coverage with small baseline, so a broad area, but also some more noise as well. Yeah, the rapid SAR approach, just to mention that briefly. So this also basically a small baseline approach, but it uses a different approach to identifying coherence. So it estimates coherence for every pixel in every image by identifying sibling pixels for the coherence analysis. So rather than this kind of boxcar coherence analysis that Tim probably talked about, you could be a bit smarter about how you estimate coherence by using similar type pixels around. Okay, and that approach is also used, I should say, this other approach. So I'm sort of bunching these together. Phase linking, triangulation, squeeze up. These are kind of all terms for very similar approaches. And really, I guess I think of it as essentially a pre-processing step that then allows you to do time series analysis. It's a pre-processing step that's applicable for distributed scatterers, not persistent scatterers. So what you do is you can make, well, in principle, you can make every single possible interference. So you have 25 images, you can make all of the interferograms, and then calculate every pixel, the coherence, using this sort of sibling-based approach as mentioned. So this is just simply one example. Actually, this is from Sammy's paper 9 years ago. And this is a so-called coherence matrix. It shows for one pixel what the coherence is every image with every other image. So what you can see is in general, smaller baseline ones, smaller temporal baseline ones, better, have higher coherence. And those long temporal baselines have low coherence. That's expected. And the trick here is that you, some way, there's different ways of doing this. You take these wrapped phases, each pixel, and you essentially invert to generate a single primary time series. So if you just created a single primary prime series, what you see is you've got temporal coherence down here, useless. But actually, having taken the information every pixel, you can actually get much better coherence and much less noise in your single primary time series. So it's sort of, I guess you could think of it maybe as a small baseline approach where you do this inversion step on the wrapped data instead of the unwrapped data. But there's still the whole kind of, having done this, what you've got is a single primary time series. You've still got to kind of do your time series analysis, so estimating aspect. That's why I sort of introduce it as a pre-processing step. So then you can apply some sort of PS-like algorithm, right, to do your actual time series analysis of that. So you kind of like you could apply a PS type algorithm because you now have a nice single primary time series. You can apply that even though these are distributed scatterers. So that's kind of nice. Okay. And another advantage is that it helps to deal with this problem, which I alluded to already. It's the so-called fading signal or phase bias. So as well as picking up deformation, you can also get phase term due to changes in soil moisture and changes in vegetation as well. And the problem is if you make very small temporal baseline interferograms, this this effect gets magnified. So we didn't really notice this too badly when we just had data that were over a month apart between acquisitions. But with Sentinel-1, when you get 6 acquisitions, it really starts to become a problem. So in many areas, you get signals like this. If you just do a time series analysis using big spats, for instance, you get signals like this that look like substance. Typically, it looks like substance. It doesn't always. Normally, it does. So because it's due to changes in soil moisture vegetation, this really affects cropland and forest regions typically. And you don't see this effect in urban regions so much. As I mentioned already, this effect is stronger in short baseline programs. But it means if you take a PS approach or a phase leaking approach, then it's much less effective. So that's a good motivation if you want to deal with distributed scatterers in a good way, rather than just take a normal small baseline approach. You could do this phase linking. It's more intensive in terms of processing, but it largely avoids this problem. But there are other approaches too. So if you have used LixPass, there's an approach you can use. For some reason, an empirical correction approach that could be used to actually reduce that. And that's based on the fact, just skip over this. I mentioned it already, right? If you calculate these loop closures, expect to get back to, you haven't got no mapping errors, expect to get back to 0, it's around, which you won't, one, because of noise, but also because of these phase biases. So you can actually use this phase bias term within the loop closures to estimate what the bias is. That's the sort of basis of correction approaches like this one here. There's a couple of papers on this. It's not perfect. And you can see in this case, it's left some of the signal behind, right? So it's reduced it signal behind. I think the second paper, the results are a little bit better, but still not quite perfect. So it's worth bearing that in mind when you're interpreting the results of the phase bias. You can normally identify where it is by looking at the loop closures. You can know where there is a form of phase bias, at least. Okay, great. So just to summarize then, so I talked a lot about persistent scatter approaches because they're a little bit maybe harder, a little bit further removed from standard InSAR, I'd say. Anyway, they rely on these pixels which are sort of coherent throughout the whole time series, essentially. Whereas small baseline approaches are appropriate for pixels that do decorrelate in time. Hopefully not too much, but if it decorrelates really rapidly, we'll hope it's lost. If it decorrelates over slightly longer times than the time between your interprograms, time between your acquisitions, so make interprograms and use the small baseline approaches. But note in both cases, signals which aren't related to deformation can be reduced by modeling filtering. When might you use one and the other? Well, I guess PS techniques really work best in urban environments. Although you can apply in rural environments, it just doesn't work really well if you have distributed sectors everywhere. So the advantage is, because one of the advantages you can get more accurate measurements, higher resolution using PS. So if you're interested in working on infrastructure, for instance, typically PS approaches are the way to go. On the other hand, if you're interested in geophysics, where resolution is not so important, and you're often working in areas without buildings and so on, then small baseline approaches perhaps more appropriate. Okay, I'll finish there. I'll take one more round of questions. Yes.
Are there any differences between ascending and descending series? Are you combining them or evaluating them differently? Because the picture that you showed about in Turkey,
Yep.
Konya area, there's a substance there. I saw it standing thing, but not quite good. Is it in the ascending thing?
Right. I think it is in there as well, actually. I could skip that and show you that afterwards. But yeah, so the question is about differences between ascending and descending data for those online. So the normal approach is to treat them completely separately when you're doing a time series analysis. So time series InSAR do one and the other, and largely speaking, they're treated the same, right? Often the ascending, the ionospheric signal is slightly worse or whatever, but basically they're the same. So it's sort of a post-processing step then to try and derive the vertical or the express. So yeah, in the case where you have substance, you'll see that in both ascending and descending. But one slight complication is because you're seeing horizontal as well, the way that horizontal maps adds to the vertical will be different from the two. So in some cases it might cancel more on one side, and then on the other side of the substance fold it would go the other way, right? So you do see a slightly different signal in both of those. So yeah, maybe that explains it.
Yeah, what about the finals that usually is annual or semi-finals? How do you evaluate?
Oh yeah, so well, if you get to the end of your time series analysis, then you have a time series, right? Actually, I didn't show any good examples of that. We have lots of good examples from Mixpass, for example, where we see these, certainly the annual signals, semi-annual signals, maybe not so much, but certainly the annual ones. So you can indeed then just model that, of course, as you might do for GFS, for example. Yeah, but going back to the PS, the first PS approach I talked about, you can also include that in your modeling. Right? If you think it's a strong seasonal one, you can include it in your modeling as well. It just makes it slightly harder to do it. Yeah. Question?
No question.
Yeah.
Is there any way that strong time series you can have multiple data, like latitude, longitude, time, and pixel value?
Yes, absolutely. Yeah. So, one of the outputs of your time series will indeed be the location of each of these pixels. So, and you've actually got 3D, right? So you've got that long and height as well for each pixel. Yeah, and then the time series itself. That's the kind of the output that you want to use. Yeah. Good. Yes.
Yeah. Do you need a reference point in this model?
Yes. I mean, at some point, you always need a reference point, right? Because it is a reference area. You have to refer your results in InSAR to somewhere. So at some point, you always have to pick that. In PS, it's more, it's the first PS approach, part of the processing to actually identify, typically. Whereas with this approach, you can swap it around, right? So you can get your results from a STAS approach, and then just say, well, I want to make this the reference, or I make this the reference, and it will just change your clusters accordingly. But you have to have a reference to actually kind of interpret.
I have two more questions.
Okay.
Regarding the temporal baseline, so if the coherence allows it, so how big should it be?
Oh, well, in some cases, there are some areas that really don't decorrelate much in time at all. They're desert areas. And you can make a really nice program over 5 years, in extreme cases. So, yeah, it's very variable, essentially depending on vegetation.
Okay. And with this approach, can you also create like a graph as you show in the ES approach that you see the rate variance through time? Yeah.
So we say graph. So the rate varies in time for each individual scatterer. So you can make a plot for each scatterer.
You show that for the teams.
Yes, and also I'm not showing you. I should show you an expressive. I think I showed one. Maybe I didn't. I think you're right. Okay. Anyway, yes is the answer. You can make from both. I mean, eventually, when you've got the output, it sort of looks the same, right? For both PS and SPAS. Every pixel that you've actually got results for, you have a time series. You have its location, you have its time series. Yeah, sorry if I didn't show an example of that. Yes.
You said about the small baseline approach can be applied to general scenario. And real severe atmosphere, for example, rainy season, like the 3 months rainy seasons in that area, decrease the accuracy.
Yes. So actually, normally the accuracy is mostly associated with the vegetation itself.
Yeah.
But for sure, if you have stronger atmospheric signals,
Yes.
then that also affects it as well. And I mean, you can often see these seasonal terms strongly reflect the atmospheric term. There are other atmospheric effects. People know a lot more about atmosphere than we should do that. Any other questions? It's that time for coffee.
Yes, I think so. Great.
Okay, thanks for listening. Good luck.
So we have coffee and tea outside, and then we should start at 4 the next lecture, I guess, if 5